Okay, so there's been many people who have contributed to these slides and how to use Rock Prof. Their names are listed here, and we try to improve this with every presentation. This presentation is from a presentation at Lumi a couple of weeks ago, and so the Lumi system is very similar to what Photonics looks like. Let's see if it'll advance. So Rock Profiler is basically a tool to extract the hardware counters from the AMD GPUs. It gathers the data, and since it's a counter, it counts every event that occurs for that counter that you ask for. It's distributed with every version of ROCm, and for this workshop, we are using the one in ROCm 502. So there's been a lot of advances since then. We're going to try to get installed a newer version as time permits. But this will show you the basic capability, and it's quite powerful even in this version. And the profiling is done with Perfetto, which is a visualization tool in the Chrome browser. So it doesn't actually go out over the internet, but it uses some of the internals in Chrome to display the traces from the profiler. So there's the first decision you need to make is which of the tools to use. So Rock Prof is a lower level tool. It's designed to get the hardware counters and then display it in a trace format. It's very effective when you want to get information about your kernels. And so that's often the starting point for anything you want to do. And in fact, I would recommend it as a starting point because it's less overhead, it's easier to use than the other tools. And then as you need more information, you might move to Omnitrace. So Omnitrace came out in about November. We're still still trying to develop more training materials with it. And it's under very, very active development. So we have one of the latest versions of it installed on your system. And we have installed versions of Omnitrace and OmniPerf, which work with 502 ROCm that we're going to use during this work. So it's we may see some issues sometimes when there's a mismatch between the current version of Omnitrace and the older version of ROCm, but it's generally pretty good. But you want to try to stay with the latest versions of these because they're changing so fast. And one of the things I want to point out is that Omnitrace and what we're going to see next, OmniPerf, are out of the research division. They're aggressively developing this, and there is a GitHub site for each of them where they are taking input and fixing it as fast as they can, or improving it as fast as they can. So in the bottom of the slide, you see sort of a sample of the trace output in Perfetto. So it still uses Perfetto, but it's going to give you more detail. It's got more collection data than Rock Prof has on its own. So it can gather information about what's happening on the CPU, what's happening with MPI. It has a COCOS interface. And so you can get a lot more information from it. It is, it may take more overhead and more time to collect information with it than you would do with Rock Prof. Now, Rock Prof does have a very similar trace for, view as we're seeing in the bottom, the center bottom, but it doesn't have as much information. OmniPerf is really a performance tool, a profiling tool. So it's going to give you data about counts, of, what your bandwidth is, how many flops you're executing in a kernel, and, what the performance is relative to the maximum for that item. It can generate a roofline, and it has several different outputs that we're going to go over. Some of them are text, some of them are a lightweight GUI, and some require a external graphics tool. So, approach these with your question. What is your question? And that sort of drives which one you should be using. So if you're just trying to figure out where the next item you want to work on, a simple tool may be better. If you want to do a detailed analysis of what's going on in your program, you may want more information to understand what's going on. And so in the past, the only option we had was Rock Prof. And that was kind of a heavy lift for Rock Prof. It generated a lot of information, but it really wasn't designed for all these different tasks. And so now you've got a couple of different options that you can add to the Rock Prof. So we have the OmniTrace and the OmniPerf. Choose the one which fits the questions you have. So, don't feel like you have to use the most powerful if your questions are fairly simple. Where do I focus my time? But if you want to dive in deep, you've got tools to do that. So RockProf lives in the ROCm directory, which on the standard install is /opt/ROCm bin RockProf. If you've got a module, it will set the path to that executable. You have quite a few options that you can use, and you can retrieve those from the command line with the -H for help. And so you can get different you can modify what it's doing by using some of these options, such as base names will reduce the size of the GPU kernel names, especially if you're using C++. It can get quite long. You can get kernel timestamps. You can select what kind of output you're getting. And then the ones that really direct RockProf on what to collect are this HSA trace, which is the lowest level of the AMD stack, and hip trace, which is tracing the hip calls. You can use both of those, and then you can also use the RockTX, which is the manual markers you put into your code. And even you can trace GPU driver calls if you want. So it's a pretty powerful tool, but it is a low-level tool. Here's an example of requesting, let's get the stats out of the run. We want to shorten the names, and you can see an example of the output from one of our simple test problems. And so this gives you a pretty good idea right off the bat which of the kernels you need to focus on and which ones you can ignore. So As I was saying earlier, you can select different levels to get information from. HIP trace, if you're programming in HIP, or higher level languages. Um, if you want to get to the lower level, you can use the HSA trace. And you can use combinations of these. And for OpenMP offload, HSA trace is recommended. So once we run that command and are executable, we can get a JSON file that we can then download and view in Perfetto. That simply bring up the Chrome browser, go to this web address. It will pull up the user interface for the tracing tool, and you can load your JSON file into it. So that here is the open trace file. There's some other things you can query in the trace. Once you load that trace, you will see some timelines of what's happening in the system. And if you want to see the kernels, you go down to this GPU item at the bottom of the trace. And if you expand that, you will see all the traces that have executed. You can also see when when copies are made to the GPU. And so it can give you a really good idea of what's happening. So this top line, we're seeing the HIP API activity. We see HIP memset. We see GPU activity in these bottom ones. And we see a copy host to device and device to host. And so one of the things you would typically do is try to reduce the copies back and forth to get better performance. You can use the W and S to zoom and the A and D to move right and left so you can explore the kernels. And as you expand it out, you will see text in each of the blocks telling you what they are. You can also see dependencies, as we see here, HIP launch and then the Jacobi. So you can see those links. If there's a dependency, that can tell you if something is holding up the operation of your kernels. And this little thing down here in the very lower right corner, I would never have known I would never have even seen it if somebody hadn't pointed it out to me. But if you click on that, it's going to show you all this information about the kernel. You can also get this by clicking on the box with the kernel name in it. But this is quite a lot of helpful information. So you can see how long it executed. You can see what the dependency between kernels is, and you can get even more information out of here, like your vector registers, I believe, shows up in the current version. So you can add your own markers. This can be quite useful if you're going to try to look at a particular function that you're working with. So you can mark the start and the end, and it will show up on this trace as well. Okay. So what are the hardware counters that we're collecting? and what do they tell us? So you can select from a list of hardware counters for the GPUs. It's somewhat dependent on the type of the GPU. And as time has gone on, they've added more hardware counters. That's perhaps the biggest advantage of getting a later ROCm version, is that you get more counters. So you can have a file with the list of counters that you want to work with. And shown here in the middle is these PMCs. Those are the performance counters, and you can make lists of those that you want to collect. So, like most hardware counters, you can only count so many in a single pass of the code. There's a limited amount that the system will let you count during a run. And so the way they do this is they run multiple times to collect all the information you want. And so when you're collecting information for a trace profile, you want to think hard about what data you really want. And you want to run a smaller problem than you may think you are first interested in, just because it can take a while to make these multiple passes and collect the information. So, you have to start getting an understanding of whether you're interested in memory, if you're interested in the floating point instructions. And you see some samples here of different things you can ask for. And then it will output the information for all the requested counters in the output in a CSV file. So here are some commonly used GPU counters. So the arithmetic logic units, the ALUs, we want to see if they're busy. We want to see, how much memory is being read from global memory and how much is being written out. We want to see what our cache hits are, and you may want to see if there's a lot of stalls in your application. So it does take a little bit of time to get to understand what gives you the best information for your application, because all the applications are a little different and have different performance limitations. So the hardware counters are global, so we recommend that no other applications are using the GPU when you're doing this. And you can get the kernel's runtime by taking the end value and the beginning value of the kernel. And the stats column will include that information. So it is aggregated over the repeated calls. And so you may want to understand at some point if there's some variation in the runtime. It does report the min and max values in some of these files. MPI ranks are a little more challenging with Rock Prof. You can create a helper script to help merge these different traces together. It takes a little bit more effort, but you can merge them if you want to get if you want to combine all the traces from all the MPI ranks. You can visualize them as individual ranks as well if you choose to do that. So then you'd want to put it in different directories so that they don't collide with each other. So here's that little helper script. it's somewhat complicated, but
Okay.
you know,
No,
you
I understand. I thought maybe we'll all the process
just
like this.
include it
Okay. Yeah. Okay. Okay.
in your
See,
just copy it to your directory and include it in your execution command, and then you can merge all the MPI ranks together. So you can see it is writing out information per rank to different directories, and then it's going to merge them. So you do have to be somewhat cautious if there's an overhead with the profiling. Rock Prof actually is very efficient, but if you insert a collection in a critical small kernel, it may cause the run to be much longer. And even more importantly, you do have to watch that you are not collecting so much information that you can't visualize it. There is a limit to how the standard Perfetto can display information, and it can run out of memory. So you want to at least start out fairly small. We do have some work going on to be able to read in larger trace files. But it gets really hard to even understand the visualization if it's too big. So you want to try to isolate the information you want to look at. That can be difficult in a larger application. So RockProf is a critical tool for understanding what's going on with your application. It's open source. It's really driven by the command line, so it's quick to use. And then we have many other tools that are built on top of it. It gives you information about the GPU kernels, each kernel, and the calls that move data back and forth or operate at the HIP or the HSA level. So you can collect hardware counters. It is additional overhead, but it can give you much better insights into what's going on. And then you can download these traces and view them in the Perfetto user interface. It's also very useful to get in the habit of looking at these text output. You can get a lot of information very quickly. I tend to favor command line interfaces and text just because it's so much quicker to work with them. And so I would not ignore the value of those formats. Okay, I think that's it for that presentation. So take questions on it.
Yeah, if there's any questions, feel free to unmute or feel free to put the question in the chat.
I have a question. So I wonder, is there a way to get occupancy directly, like from the Rock Prof or others profilers, or I'm supposed to calculate occupancy by myself?
So NVIDIA made occupancy really high profile. You can get that from, the value busy, whether you're keeping the CU units busy. Performance is really fairly complicated on the GPU, so it's more than just occupancy, but you do want to have enough work to keep all the CUs busy. So you can look at that output to see if you're keeping them busy. The other tools have even a better presentation of whether how well you're keeping those CU units busy. I do know some people that have developed occupancy spreadsheets for the AMD hardware, and that can be a helpful tool, but I do think you need to look at performance as a much more complex situation for GPUs. There's a lot more involved.
So can you share that occupancy calculator if you have as a sheet?
I will try to get that. I do not have it. I do
Okay.
know somebody who's been doing that.
Thank you so much.
Thank you, Bob.
Go ahead, Alexis.
Yeah, hello. I have a question about the analysis on the CPU side. Can we use these tools for using analyzing CPU code? I'm just wondering a general idea of porting a code from CPU to GPU and having just a single tool to go the whole process. Is that possible?
Right. So you can get some information about the CPU, but the AMD Microprof is really the tool designed for the CPU. OmniTrace does get data from Microprof. So sometimes you want to know both the CPU and the GPU, and that's a slightly different problem, and OmniTrace is really designed well for that. If you just want CPU, you may want to try the Microprof tool.
Thank you.
I'll just add that with Microprof, we can also get some tracing and profiling from uprof. So can use it for CPU and GPU, but it's not meant to be an end-all for similar to RockProf and the other tools, but you can do both from uprof.
Great addition. So the nice thing is that, you know, they give you a little bit of information about the other domain, but if you really want the kernel information, you're probably going to want to go to these tools.
Just clarifying what the HSA trace and HIP trace options do again. So which one do I need in order to profile a kernel?
The safest thing is just to specify both.
Just both all the time? Yep.
Yeah. So if you're in the HIP layer, doing HIP programming, HIP trace will get you the information. HSA trace is the lower level, sort of like
Right.
intermediate level. But if you're doing something like OpenMP, it may be doing it in the HSA level and bypassing HIP.
Good, thank you.
Okay, so if you go ahead and log into Satonix with that username. Do we have the passwords out yet? Okay, it looks like many are getting claimed. I'm going to go ahead and share the HackMD. And you can pull that up as well. So to start out with, you're going to want to get an allocation with an salloc to get some interactive resources. I've got this with a GPU-dev partition. Is that correct, Dan? I think I lost Ann. So you're going to get one node with one CPU. What?
You're correct. That's GPU-dev. Sorry, I was on mute.
That works. Yep.
And then our account is courses 01-GPU. And I've just got it grabbing for 15 minutes here. So ask for what you need, but don't hog the resources. Then we're going to load ROCm 502. That I think by default is already loaded, but we're showing it just to emphasize and make sure that you're getting that 502 version. And then we're going to do all our work in the scratch space so we don't run out of space. So that is defined for you with the my scratch variable, and that will go to /scratch slash, I think it's courses01 / your username. And then you can get this exercise here. You can do a get clone of the whole site if you want, or you can just grab this particular example, the mini N body. It's fairly easy to compile this code. You just go into the HIP directory, run this little script, and it will run a bunch of different sizes of the problem. Or you can just compile it directly and test it. Once you have that done, then you can use Rock Prof with the stats option. And so it's just Rock Prof -- stats and body original and the size of the problem. Now we're running it on the front end with this example. You may want to do this on the back end, in which case we would put srun in front of it. For larger problems, you probably want to do it on a compute node. Oh, I guess, yeah, we're not on a compute node. We got an allocation. And so we don't need the srun in this case. And then you can look at the results.csv to find to get some information about the run, and that's shown here in the HackMD. So if you're in the HackMD, you can click on Edit, and you can post questions if you have any questions about parts of the example. And I'll put a little section at the end of the Rock Prof for questions if you want to put them there.
Bobby, is this page going to be like a permanent resource for the public? Like we can come back next week and see the page.
This address will stay active. George, you want to comment on that?
We will let it as it is. This will not change. You can have access any moment.
Yeah, okay. Yeah, thanks.
So I would imagine that most of you will want to copy the JSON file to your local laptop to do the viewing. It's probably too slow to do it on the system, especially if you're going to be doing any zooming or moving right or left to take a look at what's going on. So you're going to copy it with the path to the results.json file, get it on your laptop, and then you can examine what's going on. Then you can run with counters and see what more information you can get from Rock Prof. So Rock Prof is the oldest of the tools that we're going to be talking about. So it's more mature and robust at this point. And for most programs, it will be able to generate results for your program. We do get some problems with very, very complex programs or very large traces. So you may want to experiment with it on, how many counters you're going to collect, how much space you're going to be using. Okay. I'm going to pull up a browser window. So you see here that I have a browser window. I'm going to go ahead and open up the Perfetto, and I've got an old trace in here, so it's matching that already. And when I launch it, I've got this navigation on the left side. I've got the open trace file, but I want to show you, other things on here. So if you click on keyboard shortcuts, it's going to give you all the shortcuts that you can do. I can open the trace file, and let me see if I can find one. So here's a simple trace file from one of the examples. And if I click on the GPU, I can see the different kernels. I'm going to go ahead and zoom in. That wasn't it. And so I can see the different kernels executing here. And if I expand some of these others, I can see other things going on. We see the HIP layer with the HIP mem copies, and we see the HSA layer with the lower level operations that occur. So it's a fairly simple interface, but it gives you a lot of information. And if I double click on one of these kernels, it's going to give me some information here. And as I said, the PowerPoint slides, it doesn't show you all the things that you get out of here. But for example, we can get the vector registers, the scalar registers. We can get how much LDS, the scratch storage space we're using. We can get how long it took to execute. So we can get a lot of information just from this detail.
Bob, if I can add something,
Yes.
in this what you saw now in this down place, it's really nice. Sometimes, not for RockPro, for the next tools, you can profile, for example, let's say Cocos, right? And if you have some automation, you don't know, it's not hard coded how many blocks you call in threads. And you can see there this information, how this kernel was called, or how many blocks and threads it is there. And also, the HSA, although people don't know HSA, and you don't need to know, but if something is wrong with the application, is slow, and the heap seems to perform well, you should go to HSA layer. Because heap doesn't talk to the GPU, the HSA talks to the GPU. It's a layer between heap and GPU. So maybe something is delayed, not enough queues for your requests, etc. You can see HSA calls take more time, for example.
So we're going to layer this. This is your first tool, but the next tool is going to build on it. We're going to get more information from it. And as we talk about, the third tool, OmniPerf, you can get more information than you probably want in many cases. But it can be very, very effective at identifying things like efficient use of the caches, the memory bandwidth you're getting. And so I think we're going to probably do that tomorrow. Today, George is going to do the next session where he's going to talk about Omnitrace, and we're going to go ahead and do some examples with that afterwards.
So you want me to, I mean, some people are doing exercises from Rock Prof. We should wait a bit, continue, what you want.
How did everybody go with that exercise? Maybe a show of hands? Or emojis, or?
Okay, it looks like they've been able to do a few of those exercises. So I didn't get questions such as, can I use this with the Cray or Hewlett Packard?
I had to add in the HSA trace options.
Yeah, so you can use it with any of the languages as long as you're offloading. Now, this is actually a good test if your offloading worked.
Not sure if Edric and Sam might have questions. Okay, go for it.
Yeah. I've just got the trays up in Perfetto, and without expanding anything, I see that we've got lumps of color in various shapes. I don't know what the height of the bars in these lumps mean. Can you explain it?
George, what do those heights mean? It's like half height and full height at times.
I suppose it's utilization, but I need to see what's. Can you share your screen?
It's the same one that you've been doing, the same sort of trace. So I
Okay,
can,
so-
but it's a bit awkward. That's all. One moment.
Let's see if I can
let me
pull
sort
it
it
up.
out.
Yeah, Bob, if you can share.
I can share it briefly if that's permitted.
I think Bob can do it.
Yeah.
Usually say about the utilization. I mean, at least in Omnitrace from because Perfetto, we use Perfetto from 502, right, Bob?
So I don't know if you can see my screen right now or that window right now.
Yeah, you can see that. Yeah, this
Yep.
this is total utilization. Imagine when it's full, it's utilized full. Doesn't mean efficient. It means you have a lot of request. It depends what is that. It's GPU or heap API or HSA. There's a lot of them. Doesn't mean that's efficient, but if it's zero, if it's wide, there's nothing on like CPU or GPU, for example, right? Is the white space, let's say, is bad at okay, you have nothing and you do the CPU, hopefully it does something, or something like that. But otherwise, I would say that's like utilization. As you see, it's like you have a lot of heap API calls, or or it takes a lot of time and then goes down, etc. So it's nothing to, and also it's nice to see patterns, right? If you see patterns for iterative processes, you will see a lot of patterns to recognize which is the phase that fits in what time step, etc.
So, for example, if we expand GPU 06 here, we see that the kernels are squished together, which is what you want, right? There's no delay in between scheduling kernels.
That's good, for example, yes.
But we get these gaps in utilization despite the fact that kernels are running. So we're talking here about the kernels having divergence or something at the end, where they're just waiting around for one thread. Is that the sort of thing we could interpret from this?
No, it's difficult because if you expand it, the expansion is something that we really like it because there's no gap, right? So
exactly.
Sometimes we have seen that Perfetto visualize a bit weird stuff. However, from the visualization, from this plot, I would say most of the kernels are really well. Although you can zoom, right? You can zoom to see the gap.
To be honest, I've never used Perfetto embarrassingly, so I don't know how to.
Press the W, W, and then press the D to move right, D, and zoom. And you just see the gap, right?
Yep.
And if you take your mouse over the white gap and you click and you do like that, you will see the duration. But this is really tiny, man.
Yep.
On the top, you see 0.2 to 0.3 seconds, the timeline, right?
Yep.
If you see on the top. So if you zoom more, you can click on the white space of the mouse between the kernels on the white space. Now it's really tiny. You have to zoom more, and you can just take zoom more, even more. And now click on the white space from the beginning of the white space, and with click on the white space, not on the kernel. On the white space.
It's not wanting me to click there.
Click this.
But it's not doing anything.
Nothing. Okay. Then this is from Omnitrace. Then doesn't do that. Usually, when you click on the white area, you can see the duration of the gap. Okay. When you click and you take all the, but this is I saw it from Omnitrace. Maybe now Rock Prof doesn't provide that, but this is but it is more for me. For me, it's small. You know, I can see much more worse real codes with the gaps.
Oh yeah, definitely. If I were looking at this code and saw those gaps, I wouldn't be concerned normally. But when I see that there's this big gap in, as you say, utilization at the end of the kernel, that makes me more concerned as a developer.
Yeah, I understand.
Yeah.
That's why we'll see that the other tools have some better functionalities.
Cool. Well, I'll leave it there. Thanks for explaining that. Now I know more what's going on. Yes.
The Rock Prof is our product. Okay, it is our product, but it lacks some functionalities. The other tools, the next tools, are not product, but are the research tools. Which, in my opinion, they offer the option to go advanced faster because it's not product to take decisions from all the chain, let's say. But also they don't have unlimited resources for development, but it goes really well, I would say.
Thank you again.
I would recommend that you actually click on the CPU hip. Let me go ahead and share and see if I can. So if you click on the CPU hip, we were looking at the kernel, which is interesting, but you can also see if you look at the CPU hip, there's a bunch of hip mem copies going on the entire time. And so one of your optimizations would be maybe I want to get rid of those mem copies, even though it looks like it's very efficient. So that's always a good line to look at.
I admit when I was looking at the profile, seeing that pip mem copies and the compute kernels line up exactly made me suspicious. It's not, again, what I would expect.
And And I think this is a fairly small problem, so we're really not, you're not seeing a lot of gaps just because it's small.
Here, I mean, you saw the first heap memory copy takes a lot of time, right? This is the first call is on the GPU is a bit lazy. So sometimes call an empty GPU kernel to utilize, and then you will see that everything disappears. Any long call that you cannot understand why it takes so much time, etc.
Just before I pass on to Pascal, I haven't looked at the source code at all. Is this using the equivalent of coherent memory, unified memory, or is it doing explicit copies?
I think it's explicit. Explicit.
Cool. Thanks. I know Pascal has his hand up, so I'll leave off.
Yeah.
Thanks.
Yeah, I was just sorry. I've joined late, so I'm still diving in. But it was actually the conversation about the long mem copy, because I remember doing tests with a variety of different ROCms where the command of just putting like an empty kernel, right, to warm up the GPU and so on, did not actually change the length of the mem copy. The mem copy is still slow. We wrote a bunch of tests. I can even send the paper showing the results we got with MI100s and MI250s, where the first call to copies and the first call to a kernel were always slow. You just need a copy or to warm up copies, you have to have a copy command. To warm up kernels, you have to have a kernel command. It's not a command that warms up all other commands. So it's not just a lazy command. There's something else that's going on. And I'm very curious to chat with you guys maybe later on, but just show you the results we were getting with MI100s, MI250Xs. I haven't tried Cytonics. I was trying on Joey, and I haven't tried all different versions of ROCm. So it could also be all different versions of ROCm as well that changed this. But
Pascal,
we were getting
were you using, what language were you using?
using HIP. It's just
Okay.
C++ and HIP.
Yeah,
There's
because
also OpenMP overheads
Yeah.
that were surprising sometimes.
yeah, I think there's a call in OpenACC and OpenMP to pre-warm up the GPU, but it would not surprise me that there is startup code once you start accessing the GPU.
Yeah, because we
But
tried. I tried making these like small startup codes. I was really surprised when we were doing some HIPification for CUDA code that the impact of the first call was far worse on the initial ROCm HIP 150s we were using than the CUDA call. And then we started playing with the warm up to see why the overhead is so pronounced on HIP, and then tried to figure out unit tests and so on. Anyway, something to chat about because it's kind of a separate non-profiling debugging thing, but it's just something I noticed with the profilers and debugging codes.
so if we zoomed in on the HSA, we see that it's creating queues. It's doing
Yeah.
some other operations. So there's some things it has to do for the first call, allocate buffers, create queues, and those can be expensive. So the reason I think this is worth everybody knowing is that it has been practice among many to throw away the first iteration of a timing just to avoid that long startup affecting your results, or running more cycles. So Ash is asking if it's worth doing a warm-up GPU code. It may be. You may want to do a little warm-up to
I would
avoid.
definitely say so. We've got factors of, so the main thing is we had kernels that were quick, but the first call was factors of 100 times longer because the kernel call was also pretty quick itself. It would just do lots of iterations of that kernel call. So the first one was just bogged down by the overhead of constructing the queue. There's also, weirdly enough, it could be the ROCm version we were looking at. If you looked at when I put in the HSA event timer just to get the timing through HSA, right? That also just took a long time to. HSA. I would have thought HSA events are pretty quick, and they should be, but it actually took a long time to actually complete that call. A very long time to push the first event in, to sample the time taken by the first copy. which is unusual.
I don't think it's unusual. It's just
Well, it was unusually long. It was,
Yeah.
it was just
Oh.
surprisingly.
Yeah.
Not that the fact that it was long, the fact that it was much longer than I thought it was going to be. So definitely good practice to try to warm up a GPU.
So this is highly dependent on your application. If you've got
Yeah.
small kernels, that's going to be very true. If you don't have startup code and you launch directly into kernels, that's going to be more true. But it is a good thing to be aware of.
There was one other question. Sam, I see your hand up. Edric, you had your hand up. Did you have a question that needs follow-up?
No, it's been addressed in the intro. Thanks.
I just had a question about warm-up. Is there anything we can tell the runtime to, please get all your stuff together before I get on with the work that I want to do, so it doesn't influence the timing, or is it very much on demand only?
I don't think I can say. Pascal's paper might be kind of interesting on what you might want to, launch. Do a quick just a short mem copy, maybe.
Yeah, for example, if I had another thread that was doing, I don't know, reading and configures or something, in the meantime, I could be getting the GPU ready if I had a way of doing that reliably, as an example.
I mean, just to say something, I actually tried plugging away with like a task. So I was doing OpenMP, but I mean, it was basically an OpenMP task parallelism to launch something on a device and then have the other one just keep going and doing stuff.
Yep.
Which is fine, except that requires changing the source code. It would be cool if there was something that just said, "Hip, warm yourself up," and it did it.
We're going to get that from you, Pascal. We'll launch it in a separate stream.
Thanks again. Cheers.
Okay, are we ready to go into the next talk?
I think so. And thank you, Edric, for sharing your comment that you experienced regarding Marvick. You experienced similar behavior working with HIP FFT.